Hello, everybody. My name is Jan Zanitas, and I'm with the Center for Interactive Learning and Collaboration, or CILC, and I'm going to be your moderator for today's webinar. Very exciting topic of black holes, but before we get started, I just wanted to point out a couple of things for you. Down at the bottom of your Zoom screen, you can see there's lots of little options, but the one that you're going to need to know how to use is the chat button. So if you just click on the chat button, you'll be able to type in comments and questions as we go along. Before we get started, I see we've got about 26 classes on here already. That's great. If you would, teachers, in that chat box, let us know where you're from, your school name, your grade level for your students, and how many students you have. Our speakers today would love to have that information as they start their talks. So I am going to turn it over to Jim from Zoom, and then I'll see you in a little while. Take it away, Jim.
Good morning and good afternoon, everybody. Zoom is a proud sponsor of this program along with Silk. This is our second year working with the University of Arizona PIRE project and its scientists. And they have some amazing stuff to show and tell and teach. And Zoom is a video conferencing service. We're on that right now, and we love connecting classrooms across the country and the world and within your district. And with that, I want to introduce a video from one of the participants, participant schools, Princeton High School, and Mark Eastburn.
Sit tight, kids. We've got a video coming.
Hello, everyone. My name is Mark Eastburn, and I'm a children's book author and science teacher at Princeton High School in Princeton, New Jersey. I want to extend a warm welcome to everyone who has tuned into the Zoom Classroom event, which is presented in collaboration with Black Hole Partnerships for International Research and Education, also known as Black Hole PIRE, and with support from the National Science Foundation. K-12 educators like myself and members of the Event Horizon Telescope have collaboratively developed today's session, along with the complete curriculum available online, which has been crafted to meet next-generation science standards and learning objectives centered around one of the universe's most powerful and mysterious objects, the black hole. As you may see from the mural behind me, my family and I have been fascinated and inspired by the vastness of outer space and the amazing information that we can learn from it. This became even more fascinating when we saw the first image of a black hole ever produced, which made headlines around the world this past spring. The Black Hole PIRE project integrates research and development by bringing together international partners working in diverse areas, from detector development to high-performance computing to theoretical physics. As part of this session, we've developed a challenge for everyone here today. Using the full curriculum available online at the Black Hole PIRE website to predict the event horizon shadow of the black hole at the center of our Milky Way galaxy, known as Sagittarius A star. At the end of today's session, we will share the details and hope everyone here will participate and send in their work. Our speakers today are members of the Event Horizon Telescope collaboration, a worldwide effort to create an Earth-sized telescope that can take pictures from nearby black holes. In April of this year, the Event Horizon Telescope collaboration shared the first ever black hole image from the galaxy known as M87. Work is now underway to analyze data from Sagittarius A star, the black hole in the middle of our galaxy. Our two presenters today are Leah Medeiros and Dimitrios Saltis, who are members of the Event Horizon Telescope collaboration. Leah received her undergraduate degree from the University of California, Berkeley in physics and astrophysics, and her master's and PhD in physics from the University of California, Santa Barbara. She also spent significant time at the University of Arizona, Tucson during her graduate studies. In June of this year, she started a National Science Foundation postdoctoral fellowship, which she took to the University of Advanced Study in Princeton. Dimitrios is professor of astronomy and physics at the University of Arizona. He was the previous project scientist of the Event Horizon Telescope and intimately involved in work that led to the first ever image of a black hole. His research group has led the development of tests on the theory of general relativity with Event Horizon Telescope observations. He develops novel, high-performance computational tools to study various aspects of physics and astrophysics of black holes and neutron stars. And now, I will turn this presentation over to Leah and Demetrios.
Thank you, Mark, for that great introduction. This is Leah Medeiros, and I'm going to get us started giving you a little bit of the motivation as to why we wanted to take an image of a black hole in the first place. So before we start talking about black holes, we need to talk about Albert Einstein, because it was really his theory of general relativity, or specifically his theory of gravity, that predicted the existence of black holes. So what is the theory of general relativity? According to Einstein's theory, we all live in a four-dimensional space called space-time. So we're all used to the free dimensions of space that we live in, but we're also moving through time. I know that we don't usually think about space and time as the same thing, but this theory really requires that we do consider both space and time as part of the same thing. And so according to this theory, mass will actually curve space-time. And the curvature of space will then tell mass how to move. And so I have a diagram for you here on the right. What you're looking at right now is essentially flat space-time. Obviously, I can't draw in 4 dimensions, so we'll just have to pretend. But we'll see how adding a mass to the space-time can affect the space-time itself. So now we've added a mass, and you can see how that mass can curve the fabric of space-time. And so one thing that's really interesting about the theory of general relativity is that according to this theory, the trajectory of light can also be affected by mass. And so this is very different than the predictions of Newton's theory of gravity, because according to Newton's theory of gravity, since light does not have a mass, it would not be affected by gravity at all. However, according to Einstein's theory, light also has to move through a space that is curved. And so the analogy that I like to use here is the following. So let's pretend that we have a basketball and we have an ant. This ant is very well trained, and you've trained it to move between point A to point B, always in the shortest distance. And this ant is so smart that it knows that the shortest distance between 2 points is always going to be a straight line. However, if you now draw points A and B on the surface of this basketball, what will happen is no matter how hard this ant tries to move in a straight line, it will not be able to, because it has to move along this curved surface that is the surface of this sphere. And so this is obviously only an analogy, and there's a lot of simplifications here, but hopefully the idea that as light tries to move through a curved space, the light's trajectory will be curved. That idea is really the intuition that I want you guys to understand from this very simple analogy. And so we're going to see here how adding mass can affect light's trajectory. So all of these red lines that you see here, these are photons, and now we're going to add a mass, and we're going to see how the trajectory of those photons will be altered by the addition of this mass. So the fact that according to Einstein's theory of gravity, the trajectory of light will be affected by gravity, and since according to Newton's theory of gravity, the trajectory of light will not be affected by gravity, what this means is that we can actually use this to test which of these two theories is correct. And so I have a diagram here on the right. We are all on Earth, which is on the bottom right-hand corner here, and the sun is kind of in the middle of this diagram. Towards the top of this diagram, you can see that I've labeled the actual position of a star. So what's happening here is that the star is emitting light, and that light leaves the star and passes very close to the sun. So that is indicated by this yellow line here. And so as you can see, the trajectory of the light is curved due to the presence of the sun very close to the path of the light. And so what happens here on Earth is that when we receive light from a star, we always assume that that light has always traveled in a straight line as it arrives to us. And so what that means is that we're going to essentially measure the direction from which the light is coming, and then just draw a straight line backwards. And so what that means is that we're going to think that the light is coming from the location that I've labeled as the apparent position of the star. And so what this means is that you can measure the location of the star, apparent location of the star in the sky when the Earth is in this orientation, and then you can wait a few months and then Earth will be in a different part of its orbit, and then you can compare what the location of that star is when the sun is between us and the star and when the sun is not between us and the star. And you can compare those two measurements and see that the apparent position of the star moves. And so this was actually done. It was done for the first time on May 29th of 1919, just a little over a century ago. And the image that you're seeing right now on your screen, that is one of the original images that was used to do this experiment. And so within each of these white circles exists very small stars. I know it's a little hard to see, which is why I've added these white circles so that everybody can at least know the location of these stars. And the other thing that you can notice in this image is that you can't really see the sun, right? The sun seems to be blocked out. This is because we need to wait for a total solar eclipse to be able to perform this experiment. And so during a total solar eclipse, the sun moves in between us and the sun, and so the moon will block out the light from the sun almost completely. And that's really important because if the moon was not blocking out the light from the sun, we would not be able to detect the very small amount of light that is coming from each of these very distant stars. And so you need to wait for a solar eclipse so that you can actually see the stars that are close to the sun. And so, as I already mentioned, this was done for the first time on May 29th, 1919. And then a few months later, on November 11th of 1919, the image that you're seeing here on your left, this was the front page of the New York Times. And it says, "Lights all askew in the heavens. Einstein theory triumphs." And this is really what propelled Einstein into the limelight. And so again, the 100-year anniversary of this newspaper coming out was 100 years and about 11 days ago. So now that we have some background on what the theory of general relativity is, now we can finally start talking about black holes. So what actually are black holes? The definition that I like to use is that a black hole is a region of spacetime where the gravitational field is so strong that it creates a curvature that is so strong that not even light can escape. And so what makes black holes so special compared to all the other objects in the universe is their density. So black holes have very extreme density, and that's what creates this very extreme gravity that I'm talking about. So when I say extreme density, what do I really mean by that? What is this extreme density? Well, as an example, if you wanted to, for example, create a black hole out of the entire Earth, you would literally have to squeeze the entire Earth into about the size of a marble. It would look kind of like this. So it'd have a diameter of only 18 millimeters, very, very small. Obviously, us humans can't really create that kind of density here on Earth. Not only that, but we really don't want to create a black hole here on Earth. But this density is actually something that the universe can achieve very easily and very frequently. We know of several black holes that exist in the universe. Before we move on, I just wanted to clarify a couple other things. So the size that I am showing you here of this little Earth in the palm of somebody's hand, that size is actually the size of the event horizon. So the event horizon is essentially the boundary between the black hole and the rest of the universe. And so if you were to cross the event horizon, you would be within the black hole and nothing would be able to escape, not even light. It's important to note, however, that the event horizon is not a real surface. It's not that it's the surface of the black hole. If you were to cross it, you probably wouldn't even notice. But what we're really saying here is that the event horizon defines essentially a distance, where if you get closer to a black hole than this distance, then you can no longer escape. And so within the black hole, all of the mass, in this example, all of the mass of the Earth would actually be located in a point that is infinitesimally small. So We've already talked about general relativity, but there is another modern theory of physics that's also going to be very important for us to discuss today, and that's the theory of quantum mechanics. And so the theory of quantum mechanics explains the behavior of small things. So for example, subatomic particles. And I also have included here a couple examples for you. So as an example, the theory of general relativity is currently used for the GPS system. We would not be able to use GPS if we did not have a good understanding of the theory of general relativity. And as an example, quantum mechanics is very important for us to understand the details of chemistry and will also be essential for quantum computers that are currently under development. So both of these theories independently have been tested countless times. They have passed every possible test that we have been able to throw at them. However, there's a lot that we still don't understand about how these two theories interact with each other. And so there's been a lot of significant advances in a theoretical understanding of how these two theories interact. But what we're really missing is a way to test all of these theoretical understandings. And so the point here is that to be able to test how these two theories interact, we need to create either an object or an experiment or a phenomenon where you really need both of these theories to explain that object, phenomenon, or theory. And so as an example, black holes are really the perfect thing for us to use here. So the reason for that is that we already know that black holes have very extreme gravity, and so we definitely need the theory of general relativity to explain them. But as you have already learned, all of the matter of the black hole is actually contained in an infinitesimally small location at the center of the black hole. So what this means is that we have an object that really fundamentally requires both of these theories to explain it. And so it's really the perfect laboratory for us to understand how these two theories interact with each other. So many of you, I am sure, have spent some time in labs at your schools, and you probably know that these labs tend to have a lot of instrumentation. And you use that instrumentation to perform experiments to better understand whatever it is that you are studying at that time. However, our situation is a little bit different. So we don't actually have any instrumentation around our perfect laboratory. All we have is just the black hole. And there's actually another level of complication here, because not only do we have no instruments around our black hole, but our black hole is very, very, very far away. So specifically for the black hole that we have already imaged, that image that was published on April 10th of that year, that black hole is about 55 million light years away. And so it's so far that there's no way that we could, for example, send some instruments towards that black hole to be able to do some experiments with it. So really, the best that we can do is we can observe the gravitational effects of black holes here on Earth. And so the diagram on your right here, each of these colorful circles corresponds to a real star that actually exists at the center of our Milky Way galaxy. And on the top right here, the 1995.5 number, that's years. And so as I play this animation, we will see how these stars move around in the center of our galaxy. And we can see that these people, the people that worked on this experiment, tracked the position of these stars very precisely for over a decade. And what's really interesting about this is that we can use the orbits of these stars to measure the mass that is located at the center of this image at the location of that little white drawn star there. So there's a lot of mass that is located at that location, and we can use all of the information that we know about the orbits of these stars that you're seeing here to actually measure the total mass that is located at the center there. Much in the same way that we can use the orbits of the planets to measure the mass of the central of the sun in our own solar system. So for those of you that are going to also follow along with the curriculum that we have developed, the very last lesson plan that we have developed for you, we are going to give you all of the orbital data for the stars that you see here, and you will actually perform this experiment yourself. You will use that orbital data to measure the mass of the black hole that exists in the center of our own galaxy. So another way that we can try to probe black holes in space is similar to the very first experiment that I already talked about, where we use the fact that gravity can affect the trajectory of light. So we're going to use that same fact that gravity can affect the trajectory of light, and we're now going to apply that to black holes to see if we can use this fact to learn more about black holes themselves. So the first time that somebody tried to calculate what you would see if you were to look at a black hole was in 1973, and that was by a physicist named James Bardeen. A few years later, there was another paper that was also published where somebody else was also interested in this problem, and that was by Luminet. And so what you're seeing in this figure here on the right, this is from one of those original papers. And what they're calculating is what you would see if you were to look at a black hole, if there was somebody shining a flashlight on that black hole. And what they calculated is that you would see a bright ring that would encircle a dark region. That dark region is what we now like to call the black hole shadow. And what's really interesting here is that by measuring the size and the shape of this black hole shadow, we can tell a lot about the black hole itself. And so specifically, we can tell whether black holes in space behave the way that we expect them to behave based on all of the theories that we have developed here on Earth. So again, we built this entire instrument and performed this entire project really to measure the size and the shape of the black hole shadow of a real astrophysical black hole. So obviously with black holes in space, we don't have somebody conveniently shining a flashlight on that black hole, but instead we have a lot of matter going around that black hole. So all of the orange stuff that you see here, this is matter that is swirling around the black hole, falling into the black hole. And this matter is going to get very, very hot. And because of this, it'll emit a lot of light. So what you're seeing right now is the result of a computer simulation that calculated what the black hole at the center of our galaxy might look like if you were to look at it with goggles that let you see radiation that has a wavelength of 1 centimeter. These yellow structures that you see here, these are the jets of the black hole. And so what's happening is that this black hole has a very strong magnetic field. All of the matter going around it is so hot that it's completely ionized. So you have a bunch of particles that have a charge moving around in a magnetic field. And the interaction of those two things can create these very huge, powerful structures that we call jets. So now we're going to go from 1 centimeter all the way down to 1.3 millimeters. And we'll see how by going to a shorter wavelength of light, we can see through all of this disk in much the same way that an X-ray is going to a shorter wavelength of light and can then see through all of the skin and muscles in humans to be able to see the bones. Let's go ahead and do that. All of that other stuff becomes transparent, and hopefully you can see this dark circle here in the center. That is the black hole shadow. And so the light that you're seeing here, this is again a simulation, but the light here is being emitted by all of that matter going around the black hole, and we're seeing the effect of how the presence of this black hole affects the trajectory of that light. And so with this, I am now going to pass this on to Dimitrios, who will continue this talk. But as we do that, I also want to read to you a poll question. So we would like all of you to participate in this poll question. Hopefully you can see it on your screens right now. I'm going to read it to you. So we want you to guess how much smaller was the first image of a black hole compared to the size of the moon on the sky. So the first option is 1,000 times smaller. The second option is 100,000 times smaller. The third option is 1,000,000 times smaller. And finally, the last option is 100 million times smaller. So everybody please vote, and we'll share the results of this poll with you shortly.
Leah, before we move to Dimitrios, I want to let some questions be answered by you, and then we can have the results of the poll. Okay, Dimitrios, so I would like to hear from Miss Manlick's class, so the student will be asking a question. Go ahead, Miss Manlick.
Hold on one moment, Jan, I will bring her up. I'm just gonna let our poll attendees get in there. So we're gonna while we're voting, we'll bring her.
And teachers, this is also a time where you can type in your questions in the chat box, and I will relay those to Leah.
Okay, so Ms. Van Lake's class, our student is available. When she's ready, she can go ahead and turn on the camera and unmute, and we'll be ready.
Hello. Can you hear me?
Yes, go ahead.
Hello, how are you doing today?
Good. How are you guys?
We're doing great.
I just wanted to ask, do you believe that there are currently any accurate representations of what actually occurs within a black hole?
Ooh, that is a very good question. So before I answer this, I want to make it very clear to everybody what this question is really getting at. So what happens is, since no light or really any information at all can escape a black hole, it's very hard for science to be able to definitively say what happens inside of a black hole. And this is a really fundamental thing about science, is that science can really only talk about things where we can test. And so we're not going to necessarily be able to really test our theories about what happens inside of a black hole, because it's fundamentally impossible to be able to extract any information from within the black hole. However, there are many theories that do have predictions for that. And what that means is that we develop a theory and we test that theory in all the ways that we can. And then we say, if this theory is correct, which on all the ways that I've been able to test it, it seems to be correct. If this theory is correct, what would this theory predict for what happens within the black hole? And so that's really the best that we can do, just based on fundamental limitations for how black holes behave. And so based on these theories, the prediction from general relativity is what I explained to you today, that inside of a black hole, all of the matter is in an infinitesimally small location. But there are also some other theories that say that quantum mechanics might change that picture and might affect it in various different ways. And so instead of having an infinitesimally small place, you might have something that actually has a finite size due to quantum mechanical effects. So thank you so much for your question today. I really appreciate that.
Okay, so I don't see any other questions on the chat at this time. But teachers, I really want to encourage you to get your kids to ask a good question, because we're going to have lots of time for conversation at the end of the program. So now I'm going to throw it back to Demetrius, and you can hand off that poll question for us.
Thank you very much. Can you hear and see me? Excellent.
Yes.
So thank you, Leah, for this wonderful introduction to the theory of general relativity. And it's my turn now to try to explain to you how we started with those original ideas of what a black hole is, or what a black hole would look like, that shadow in the sky, and convert it into an experiment that let us take that particular picture. And the question that Lee asked you to try to guess is how small really a black hole looks like in the sky and compared to the moon. And what I see here is most of you, 61% of the people, said that it's going to be about 1 million times smaller. Okay, let's try to understand how small that black hole will look like. So to go from a theoretical idea into an experiment, we had to make a number of choices. And the very first choice is we had to pick which black holes in the sky we're going to try and take a picture of. And we chose 2 targets for our very first experiment. The one on the left is what you see when you look towards the constellation Sagittarius, the Archer, where the center of the Milky Way galaxy is. As Leah pointed out, there's a lot of stars. Those stars orbit around a black mass of something that is unknown. We call that black mass Sagittarius A star, the brightest radio source in the constellation of Sagittarius. And we think that this is a supermassive black hole in the center of our galaxy. The one on the right is the other galaxy, a very distant galaxy, 55 million light years away. It's called Messier 87 or M87. And the reason that we think there is a black hole there is because it has this little, what looks like a little jet emanating from its center. But if you think about it, this is the entire galaxy. This is a very powerful jet that starts from the center of the galaxy and moves uninterrupted for tens of thousands of light years all the way to the galaxy's edge. And the only object in the universe that we think can launch jets like this is a supermassive black hole. So these were the two targets that we started with our telescope. But in order to make our telescope take those pictures, we had to ask, just like we asked you a second ago, how big those black holes will be. And to give you an idea of a scale, I just wanted to compare what the size of a black hole would be like in the sky compared to something that we've all seen, the full moon. And the full moon in the sky is about half a degree across. You know, a circle has 360 degrees. You get half of that, and that's the size of the moon in the sky, of the full moon. But this is too big for us. So what we're going to do is we're going to take a degree and we're going to split it in 60 arc minutes, just like you take an hour and you split it in 60 minutes. We'll take an arc minute and we'll split it in 60 arc seconds, but that's still too large. We'll take an arc second and we'll split it in 1,000 milliarc seconds. We take 1,000 milliarc seconds and we will split it in 1,000 microarc seconds. And this is how small our black holes are going to be in the sky. The black hole in the center of the galaxy M87, we expect it to be about 40 microarc seconds large, which is 1/100 millionth of a degree, or about 100 million times smaller than the size of the moon. So you all guessed that black holes are really, really tiny, but the true answer is it was even more tiny than you would have guessed. And just to put it in perspective, how small would something have to be on the moon in order to appear as big as the black hole in the sky? Well, taking the picture of the black hole would be identical to taking a picture of the donut that somebody put on the surface of the moon. And you can imagine that this is a tiny, tiny, tiny feature that we're trying to take a picture of with a telescope. How do you make a telescope to take pictures of tiny, tiny, tiny images in the sky? Well, you have to make the telescope very, very big. And when we ran the numbers about 20 years ago, we realized that in order to take a picture of one of those two black holes, we had to design or build a telescope as large as the entire Earth. Now, we all like to make big projects and we're very bold about it, but you can all imagine that it's both too expensive and impractical to fill the entire Earth's surface with a mirror and turn it into a telescope. So instead, we did the next best thing that we could think of, which is we took every single telescope that we can put our hands on and was working at this particular wavelength of light, the 1.3 millimeters, every single telescope around the Earth. We turned them all at the same time towards the black holes. We saved all the data in hard drives and we clocked them, we timed them extremely accurately with atomic clocks, what we call hydrogen maser clocks. And then we sent all that data to a big supercomputer and combined them together to make it work as if those little telescopes were part of a telescope as big as the Earth itself. So we effectively use a computer to combine all these telescopes all around the Earth to make a much, much larger telescope in a technique that we call very long baseline interferometer. And what telescopes did we use? These are the telescopes that combined what we call the Event Horizon Telescope Array in 2017. And we start from a telescope on top of Sierra Nevada in Spain, telescopes in Chile called the ALMA array, telescopes in Mexico, this is the large millimeter telescope, telescopes in Arizona, just in the mountains outside of Tucson, the submillimeter telescope, telescopes in Hawaii on Mauna Kea, the submillimeter array and the JCMT, and telescopes in the South Pole. This is the South Pole telescope at the very center of Antarctica. Later on in 2018, we added more telescopes in France, in the French Alps, and in Greenland. But you see how we placed telescopes in just the right places, such that we span the entire diameter of the Earth, which was the size that we wanted to achieve in order to take a picture of something as small as a black hole. But it's not enough to just have those telescopes. You need a lot of people to go to those telescopes and run with them. And we built an entire collaboration, a little over 300 people. This is the last collaboration meeting before the announcement in the Netherlands in 2018. And we're all very happy because we had seen that the project worked before the announcement, and we had seen the picture of the black hole. And what these people did is for about a decade, they built in their laboratories all the equipment that one had to take to the telescopes and make the measurements at the right wavelength of light. You see one of those receivers on the left, and on the right, you see Professor Dan Maroney of the University of Arizona and his then graduate student, now Dr. Junhan Kim, that they're putting together the detector that they took to the South Pole. And then 4 winders, they flew to the South Pole. You see in the bottom left, the military transport that takes you to the center of Antarctica. You see in the bottom right, the cargo place where people and equipment are put together, not exactly your business class flight to go to the South Pole. And there is Dr. Kim in his penguin outfit at the geographic South Pole. And you can see in the bottom left a little bit the South Pole Telescope, part of the South Pole Telescope where the experiment was put together. And this is something that had to be done from each and every one of the telescopes that I showed you before. I was fortunate enough recently to go with another student, an undergraduate student, Dalton Glove, to Greenland, only a few hundred miles from the North Pole. This is the most recent addition to the Event Horizon Telescope. And this is one of the reasons why it took almost a decade after we had identified what we wanted to do in order to put together the equipment and put together the infrastructure to make this project happen. And April 5th, 2017 came, the time that we were going to have our first observations. And you see here teams of people at the various telescopes the day of the observation. Upper left is in Chile. The upper middle is in the South Pole, and going around is Arizona, Spain, Hawaii, and Mexico. Dr. Medeiros and I were actually in Cambridge, Massachusetts that day in a control room where we're trying to make sure that all the telescopes were working correctly and were ready to observe. Everybody is extremely happy because we were worried whether we will be able to have good weather simultaneously in all places around the Earth. And this was one of the unbelievably lucky occasions that the first day of the campaign, we had the best weather that we could ever have imagined. We waited for the night, to come by, and this is the South Pole Telescope observing the galaxy. And you know where that led to. It took about 2 years to collect the data, to transfer the data, to combine the data with the supercomputers, to analyze the data. And on April 10, 2019, only a few months ago, the Event Horizon Telescope collaboration released the very first picture of a black hole, and in the center of the M87 galaxy. And this is what we released. And you will see this is exactly what we expected. This is exactly what Einstein's theory of general relativity predicted. A bright ring of emission, which is all the hot plasma that is swirling around the black hole just before it crosses the event horizon. And that bright ring of emission is interrupted in the center by that shadow, that smoking gun of the event horizon from which not even light can escape, which is nothing but the black hole itself. We were not happy only that we could take that picture of the black hole, but we can actually do measurements. This is what we do in physics and astronomy. We like to do experiments to make measurements. And we used that shadow to measure the mass of the black hole. The more massive the black hole, the bigger the event horizon, and the bigger the event horizon, the bigger that shadow. Remember, I told you we expected it to be about 40 microarc seconds wide, tiny, tiny fraction of the size of the moon. Well, we employed a number of accurate algorithms, and I'm just going schematically to show it to you here. And we measured that the size of the shadow was 42 microarc seconds. We used Einstein's theory of general relativity to ask ourselves, how massive should the black hole be in order to generate that shadow. And we found that it has to be 6.5 billion times the mass of our sun. This is one of the most massive, the largest black holes that we know of in the universe, one way or the other. And what is more important, just like Leah pointed out, we could see the effect of the black hole on the stars around it. This is just an animation on the side. These are not real observations now. And in a statistical way, we can infer the mass of the black hole from the orbits of those stars. And we found it to be identically equal to 6.5 billion times the mass of the sun. And that let us understand that not only black holes exist in the universe, but they have the exact properties, the exact sizes that Einstein's theory of general relativity predicted more than 100 years ago. And that was a remarkable achievement for that theory. But we're not satisfied by that. We want to do something better using the black hole in the center of our own galaxy. So if you look out, especially during the summer months when Sagittarius, the constellation of Sagittarius is up, and look up, you will see the Milky Way galaxy. This is a combination of many, many pictures to see the entire galaxy throughout the sky. And what I will show you now is a little animation done by the Max Planck Institute in Munich, where they're using actual photographs at different resolutions flying into the center of the galaxy. So I will go through, you will see the constellations, you'll see all the nebula, the clouds, the stars. We're zooming closer and closer to the center, a few 10,000 light years away from us. A large concentration of stars. And when you zoom really closely in, now these are the actual pictures on which the animation that Dr. Medeiros showed you earlier, that people take with very powerful telescopes on Earth now to measure the orbits of the stars around the galaxy. And when you do it carefully, so this is from an actual peer-reviewed journal article that was published very recently, a year and a half ago, about the black hole in the center of our galaxy. When you do it carefully, what you see is those stars orbit that little empty point of space in the middle. And actually one of those stars that we affectionately call the S2 star, the second star close to the black hole, we have observed it over more than a decade. This is what you see on the right. It's its orbit in the sky over more than a decade. And we can see it make a full closed orbit. This orbit is very elliptical. You can see at the bottom of that orbit where it says Sagittarius A star, that is the location of the center of mass. That's the location of where we think the black hole is. That's where we turned our telescope to. And just like Kepler used the orbits, the properties of the orbits of planets to measure the mass of the sun, what we can do is we can use the orbits of those stars, measure very accurately the mass of the black hole in the center of our own Milky Way, and then use Einstein's theory of general relativity to predict how big the shadow of that black hole will be. And this is where we would like to ask for your help. In a handout that was part of the registration, and you're going to get a follow-up email with all that information, I think tomorrow morning, we provided you with the data from those peer-reviewed papers that have the orbital characteristics of stars around the center of the black hole. We would like to ask you, and we give you the equations and everything that you need, to use this data, to use those orbital characteristics, and tell us how big you think the mass of the black hole in the center of the Milky Way is. Do the actual measurement yourselves. And using Einstein's theory of relativity, and we'll give you again the equation for that, you can predict how big the shadow diameter will be. And if you know the shadow diameter and you know the distance to the galactic center, then you can predict how big the angular size will it be. Will it be like 42 microarc seconds, like what happened for M87? Will it be smaller? will it be bigger? And remember, this black hole is much smaller than the one in M87, which means that overall if you were next to it, it would have looked smaller, but it's also much, much closer to us than the M87 galaxy. So that effect will make it appear bigger in the sky. Which of the two win? And before you do any of that, we just wanted to ask you for a guess, for another little poll question for you to think about it. So could you guess, after you do that analysis, how will the image of the black hole in the center of our Milky Way, Sagittarius star, compare to that of M87? A, will it be much larger than that of M87? B, will the image of Sagittarius star be much smaller than that of M87? And C, will they be about the same? So why don't you give it a shot, make a guess now, and then help us to find out what the true size of the shadow in Sagittarius star will be if Einstein was right. What we would like you to do is follow the outline of the handout that you will also receive tomorrow and submit your work to an email address that will be in the handout to us by December 6th, 2019. That's about 2 weeks from tomorrow. We promise that whoever people or class sends us any information, you will get back a personalized autographed picture of the first black hole picture from M87. We will use your results as we now have the data and analyze, take the picture of the black hole in the center of the Milky Way. And when the Event Horizon Telescope collaboration announces those results, then you will be there hopefully to see how big the shadow turned out to be, and you will know by yourselves whether Einstein was right or wrong. So that's all I wanted to say, we wanted to say for today. And I just wanted to thank the 3 high school teachers that helped us really tremendously in putting this together. Juan Botella from New York, Mark Estburn, from whom you heard earlier from Princeton, New Jersey, and Helen Reynolds from Tucson, Arizona. I would like to thank Rossi Johnson, our project manager, for making that happen. And of course, I would love to thank Zoom and CILC for organizing this and making it work. Thank you very much.
Thank you, Demetrios. So we've got a couple of questions that I'm going to give to both Leah and Demetrios. And teachers, this is your time to put your own class's questions into the chat window. So first question, what is the biggest black hole that has been discovered?
Should I take this?
Yeah.
So the biggest, by the way, I just saw the poll results. Thank you for sharing them with that. And I see that it's 50-50 split that will be either much larger or much smaller than the black hole shadow in M87. Okay, I do not know the answer. I honestly do not, because we're now in the process of analyzing the data. We don't know how big it's going to be. We will know soon. And sometime in the next year, 2020, we will make that announcement and we'll all be there to see it. But how about the biggest black hole that we know of? There is a black hole in a distant galaxy that we know of its existence because, again, of the influence, the gravitational influence on the stars in its vicinity. And the record so far is about 100 billion times the mass of our sun, which is about 10 times, a little over 10 times larger than the black hole in the center of M87. You might ask, why are we not taking a picture of that black hole? Well, that black hole is so farther away than 55 million light years that we don't believe that we will be able to resolve the shadow with a telescope as big as the Earth. Maybe 10, 20 years from now, maybe one of you high school students will be the ones that will take the Event Horizon to space, the Event Horizon telescope to space, and take that picture and show it to us.
Thanks. So next question, how long would it take for a ship to reach a black hole, and what is the rate of acceleration you would have to travel to reach it?
Go ahead.
Do you want me to take that one? I'm happy to. Okay, so one thing that is very interesting and is actually the reason why I became so interested in physics as a high school student. So there's this whole other theory that we didn't get to talk about today that's called the theory of special relativity. And that's also one of Einstein's theories. And I think that if you ever are curious and if you're interested in this, at least for me, when I was a high school student, it really got my mind going and really got me excited about physics. And so your question is actually very relevant to special relativity. And so what special relativity says is that nothing can move faster than the speed of light. And so this is really a fundamental law of the universe, as far as we can tell, based on all of the tests that we've been able to do. And so nothing can move faster than the speed of light. And not only that, but if you have a non-zero mass, which a ship would have a non-zero mass, you will never be able to move at the speed of light. It would essentially require more energy than the entire energy content of the entire universe to move anything with non-zero mass to have the speed of light. And so, for example, for the black hole that is the black hole that we imaged earlier this year, that's 55 million light years away. So it takes 55 million years for light to reach us from that black hole. But if we were to have a ship, there's no way that we would be able to move at the speed of light. So it would take us way longer than 55 million years. And so the details of exactly how long it would take and what acceleration you might need definitely depend on the specific details of your ship. But as a ballpark estimate, I think it would be impossible to make that journey in less than 100 million light years, just as a general estimate, without knowing the details of the ship that you have in mind or your propulsion mechanism. But definitely let me know if you do have this plan, because we should maybe talk about the details of that.
That's a long trip. Okay, next question. I have two classes that want to know how many black holes have been discovered to date.
I can take that. So there are two types of black holes, and we only talked about the supermassive black holes, the ones that are in the centers of galaxies that have millions and billions times the mass of the sun. In every single galaxy that we looked at with proper telescopes and good enough resolution to see the gravitational effects of whatever is in the center, we have always found a black hole, a supermassive black hole. So even though we cannot tell for a fact because we haven't looked at 100 billion galaxies, we think, and our theories predict, that pretty much every single of the hundreds of billions of galaxies in the universe will have a black hole in the center, in the known universe. But then there's another type of black holes. These are black holes that are formed when individual stars that have, say, 10 times the mass of the sun, 20 times, 30 times the mass of our sun, collapse at the end of their lives. We call them stellar mass black holes. And we know of about 25 of those in our own Milky Way, but we really think that there's millions and millions of those. It's just that they're extremely difficult to find because they're really small and they do not emit, for obvious reasons, any radiation. So I would say millions and millions of small black holes in every galaxy, and a supermassive black hole at least in the center of each one of the hundreds of billions of galaxies in the universe.
Okay, why do black holes evaporate?
Yeah, you want to take that?
Yep, I can talk about this. So if you remember at the beginning of my talk, I was talking about how black holes are really the perfect place for you to learn more about how the theory of general relativity and the theory of quantum mechanics interact with each other. And so if you remember that, your question is actually really perfect in that context. And so a few years ago, Stephen Hawking calculated a few details about black holes, taking into account the fact that black holes live in a quantum mechanical universe. And the fact that black holes evaporate is one of those effects of dealing with black holes in a quantum mechanical universe. So to have a black hole that evaporates, not only do you need the theory of general relativity, but you also need the theory of quantum mechanics. And so to fully understand this, it is very complicated, but I'm going to try my best to give you a short, simplified answer. And I definitely encourage you to try to learn more about this yourself. And so what happens is that according to quantum mechanics, the vacuum of space-time, which is really just the emptiness of space-time, due to quantum mechanical effects, we have a lot of what we call virtual particles coming in and out of existence. And so what this means is that quantum mechanics can just create a pair of particles in space, and they will have opposite charge and be opposite in a few other ways, but this is something that the theory of quantum mechanics can do, and this is something that we've actually been able to observe with experiments in laboratories. And so essentially, what happens here is that in vacuum, when you don't have a black hole, by creating a pair of particles, all of the things that need to be conserved in the universe, when you create that pair of particles, they will be opposite in every way, such that you are still conserving all of the quantities that need to be conserved. So for example, momentum needs to be conserved, charge needs to be conserved. However, if you were to create those two particles close to a black hole, one of the particles might fall into the black hole and the other one might escape to infinity, infinity in quotes here. And what happens is that breaks the symmetry. Okay, and so you no longer have created two particles that are perfect opposites of each other, but now you have a situation where one of the particles can go on and survive for a while, whereas the other one has fallen into the black hole and is lost forever. To fully understand the details of this, you definitely need to understand a lot of quantum mechanics, because it's actually a really beautiful result, and there's a lot of really interesting aspects of this, but that's kind of the general idea. And again, the main point here is that this is an effect where you need both quantum mechanics and general relativity to understand.
Thank you, Leah. Folks, it looks like we're about out of time, and I still see some great questions that haven't been answered, but we've got to go. I would like to thank Leah and Demetrios one more time. It was a great program with lots of good information. And we might just send you some of these questions later on if you're open to that.
We would love to answer them.
Good. Teachers, thank you all for hanging in with us for the whole hour. And be sure and check back on CILC for upcoming Zoom webinars for you. And then finally, be looking in your email tomorrow for an evaluation of this program. This helps us to make the programs better every time we do it. So with that, I will leave you. Thanks everybody for coming. Bye-bye.
Bye.
Bye-bye. Thank you for coming.